Okay, guys, so welcome back. Today we continue with lectures 14 and 15, numerical linear algebra. And as we covered last time, the system, how to solve systems of equations, and we talked about Arnoldi vectors and how do we generate them. And I'll go through a quick review and just expose a couple of new concepts. So we said last time that big data mainly deals with large, huge matrices and tensors. And it's often a problem to even to solve linear systems and or find eigenvalues and eigenvectors or singular vector decomposition for such matrices. Okay, so the goal now is to deal with the problems from a numerical point of view. And I gave a small example on how to split a matrix in a way that we could be able to iterate and solve a linear system. And we talked about what we call Krylov subspaces. And we said, just to give you this summary, the Krylov subspaces, its intention is to reduce the size of a problem. On a problem where we have to compute the largest eigenvalue and the corresponding eigenvector for a huge matrix. Okay, and for the guys who asked about how to deal with big data, so here we are dealing with big data. Huh? So and the idea is that now to deal with the Krylov subspace, we have to generate an orthonormal basis. So this is exactly what the Arnoldi iteration does. And we talked about the Arnoldi iteration, how it performs, how it is one of the most, in fact, powerful algorithms in numerical linear algebra. Okay, so I'll go and continue with Arnoldi iteration. And we gave the matricial formulation of the Arnoldi iteration. And we said that at the end, that the most important thing is that the matrix you will find at the end, which is HK, is the projection of A onto the Krylov subspace. And in fact, you don't need anymore to compute the eigenvalues of A and sort them and take the largest one. You just need to compute the eigenvalues of H and take the largest one. And this would act as an estimation of the largest eigenvalue of A. So to continue with this, that was the last point here, in fact. We said since H is a Hessian matrix, it's easier to compute the eigenvalue of H than working directly on it. So what I wanted to show you right now, since the guys have been asking for more computational stuff, so I'll share with you just a smaller problem than the one we've seen last time, which was quite large, where we had the 10 by 10 matrix. So this time, I'm sharing you the same algorithm, but applied. So it's exactly the same algorithm. I didn't change anything. I just changed the matrix. Okay. By the way, I would like to open a small window, let's say here. The way we are entering the matrix here is not practical at all. You have to understand this. You have to deeply understand when you have to deal with large matrices, you're not going to enter them one by one or row by row. Okay. So you have to just write a function that reads a file at the end, okay, or imports a file. And I will show you how to do this. Here. But here, since we are seeing things from an academic and pedagogical point of view, so I would like to see them, to print them. Okay, I would like my students to be able to, change the code by themselves, see how it behaves. So here I'm now giving myself a 5 by 5 matrix, and the goal is just to see how to estimate the largest eigenvalue for this 5 by 5 matrix. Okay? And as I said here, I said that, well, it is expected that the matrix H I obtained has a largest eigenvalue that is quite close to the largest eigenvalue of A, and that's all. So here I'll be running my algorithm just based on that fact. And I'm expecting, of course, the largest eigenvalue of H to be very close to the largest eigenvalue of A. And this is exactly what happens here. So after doing my computation, so what I'm doing basically here, I'm projecting you see the application window, guys, huh? You see the execution.
Yes, Doctor. Yes.
Okay. So what I'm doing. So the 5 by 5 matrix is projected on Krylov space of size how much? 3. Okay. So I'm reducing the size of the problem from a dimension 5. I'm moving to dimension 3. Okay. So the H matrix here will have just let me see this. The H matrix will have 3 eigenvalues and 3 corresponding eigenvectors. So for H, this is H I obtained here, where it is. 3 by 4. Yeah, so this is H 4 by 4, sorry, because they're adding 1 here. So you see the largest eigenvalue, because they give them in ascending order, from the lowest to the highest, is 897. While the largest eigenvalue for the real A, for the exact A we entered, is 939. See? So just in 3 iterations, they were able to, the algorithm was able to estimate this largest eigenvalue with 897. Of course, if I'm taking the rank 1 matrix, the A1 that estimates this data matrix, it would be quite close. Okay? If I just perform an SVD decomposition on H, it would be very close on to the one I will get for A. You get my point, guys? And that's it. So here I close the talk about, and I just uploaded this file, by the way. So here I close the talk about the Arnoldi iteration, and I will continue based on what we just learned on how the Arnoldi iteration performs. So we were saying that Arnoldi iteration is one of the most powerful algorithms we have in numerical linear algebra, and but it is just a beginning to do other things. So, for example, we can use the Arnoldi iteration to solve what we call just linear systems now, and this is exactly the goal of GMRES. In fact, GMRES stands for, sorry for that, stands for generalized minimum residual. Okay, generalized minimum residual. So the idea mainly is to solve AX equals B and to find the vector xk that minimizes the distance between B and AXK. Okay, so in fact, we are doing an estimation of the exact solution to B. Why an estimation? Because A is too large, and you cannot just claim that you have an exact solution, or you cannot just maybe work on the inversion of A. So you are going to estimate the solution by xk. Okay. So what it does, it uses the orthonormal vectors you generated with the Arnoldi iteration, and you want to find to find the yk that minimizes. Sorry for misspellings. There is a couple of misspellings. I'll correct them later on. To minimize the length of what? Of this distance. And we iterate. So finding yk is a least squares problem, in fact. So we'll be minimizing the least squares distance from xk to the exact solution of the problem. And the zeros below the first subdiagonal of H of this matrix, we generate hk plus 1k times y, the one we generated, make what we call the GMRES especially fast, because we are dealing with a sparse matrix. Okay. Now I will move on to another extension. So the last part of the talk is about extensions of numerical linear algebra. First of all, what happens if A is equal to S? Symmetric matrix. In that case, in fact, you will end up with the H matrix, which is symmetric. So we say, in fact, that H is tridiagonal because only one diagonal above and only one diagonal below. So the Arnoldi's iteration needs only just one autoregressive step instead of rolling over all preceding preceding vectors. So in that case, we call it the Lanczos algorithm or Lanczos Iteration. So here it uses simple letters A1 to AK instead of Q1 to AK on the main diagonal, and B1 to BK minus 1 on the diagonal above and below. The A's and the B's, in fact, in T replace the H of the Arnoldi's matrix. And this is about the Lanczos iteration. Okay, I will upload later on a way to implement, inshallah, the Lanczos iteration. So just to give you an idea, this is the step. You see there is no J loop. Compared to the Arnoldi iteration, there is no J loop. Okay, so and the articulation step is mainly. So remember, in the Arnoldi iteration, we started with B, such that the initial vector we generated is B over norm of B, and then we generated a new vector B, which was A times Q0 here. Okay, here we're doing exactly the same thing, but S stands in place of A, in fact. Then we extract the diagonal, okay, from this matrix, from this vector Q, K, T times V from this matrix, and we use it to find the orthogonalization in one step instead of doing it in 2 steps. Okay, then we compute the norm of the new vector obtained, and we use it to generate a new vector Qk plus 1, and it works quite well. Okay, so this is the mathematical thing. These are the mathematical things about the properties of the matrices you obtain. So at the end, to summarize, you obtain a matrix T, and in fact, a solution that that estimates the solution to the exact system you have. Okay. Right. The next iteration, the next extension, is what we call conjugate gradient, and I'm pretty sure you've heard about it. You heard about conjugate gradient before, Kaczmarz. If you did linear on linear optimization or linear on linear programming. So nobody is answering. I'll answer myself. Yes, you heard about it. So mainly the conjugate gradient, CG, for conjugate gradient algorithm applies to, in fact, what we call symmetric positive different matrices. And remember, we said we love these matrices. Why? Who can help us? Why do we love symmetric positive different matrices, guys?
Because it's diagonal.
No. وينه فراس اليوم؟ وينه عبد الله؟ Okay. We love positive different matrices, Ya Abdul Aziz, because they have. Yes. Who said this?
Jalud. Hamid Jalud.
أهلا محمد. شكرا. Yes, exactly, because they have positive and real eigenvalues. That's why we do love symmetric positive different matrices. So theoretically, this CG algorithm, it gives the exact solution in n steps. Theoretically, but those steps are slower than elimination, in fact. But practically, it performs very well. The same thing happened, in fact, in history of solution methods. The same thing happened with the simplex algorithm. Theoretically, the number of iterations is quite high, but practically they perform very well. Okay, unless on very specific case of problems. So CG is one of the very best algorithms, in fact, when it happens to solving problems or linear systems with positive definite matrices S. Okay, so this is a particular case of the Lanczos algorithm, particular of a particular. And because S is positive definite, in fact, what we do, we can compute what we call the S norm to measure the error after n steps. The S norm is given by xt times Sx. And in fact, the kth conjugate gradient iterate, xk minimizes the error between x, the exact solution, and the solution we estimate over the K-Kirillov subspace. And after K iteration, you are dealing with the K-Kirillov subspace. So in other words, the combination x and xk, this is again another mistake. X and xk is the best combination of b, sb, sk minus 1, b. Yani a best combination of the vectors generating the Kirillov subspace. So the algorithm starts mainly with the following initialization. So we do have an x0, which is the initial vector we start with, as usual. Let's set R0 to 0 and D0 to R0. And we just iterate n iterations. So we do compute alpha k, which is just, and since we started with an initial x0, we do compute rk minus 1 times rk over dk minus 1t times sdk minus 1. Okay? And this is, in fact, the step length when you move from xk minus 1 to xk. Then you find out the new value of xk. How? By taking the old xk minus 1 and adding the product alpha k, the step length, by the direction in which you are going, multiplying by the direction, dk minus 1. Okay? So you approximate the solution. And here you approximate the new residual, which is b minus sdk, which is equal to rk minus 1, the old residual, minus the step, times sdk minus 1. Okay? And now you compute what we call the improvement step, because this is not enough. You have a correction to your step. So you compute bk, which is equal to rkt times rk times rk minus 1 over k minus 1, a kind of correction or coefficient of correction to update what we call the direction to be used for the next iteration. Okay? So every time you are updating the iteration, the direction, using the previous information you obtained from the residuals. You see? So the residuals, they do tell you, this is the beautiful idea. The residuals, they tell you if you're doing in the right direction or in the wrong direction. So basically, this is why, in fact, it's a kind of a data-driven algorithm inside it. There is a kind of intelligence inside. You get my point? The algorithm itself is not blindly working. It corrects itself. واضحين شباب? Why now the question? I'm sure you should have seen something that looks like this before in a very, very, very common course in mathematics. Which one is it? Especially this Math
1.
Math 1. Which algorithm?
Math 1, Doctor.
Which algorithm? Which thing you've seen something like? Where did you see something like this? Which section is that?
In the last sections about the integration with 3D.
Okay, maybe Abdulaziz, but I was just talking about. In fact, my intention. Yes, Khalid.
Math 101 approximation Newton's.
Exactly, Khalid. Thank you very much. Newton's algorithm, Shabab. You remember? There's a Newton algorithm to find the minimum of a function at some point. You use the direction obtained from where? From the derivative. That's it. That's the whole story. In fact, the d here is given by, that's why we call it conjugate gradient. Because the d here, what you can use, every time you can use the gradient. Okay? To understand what is the direction you should be heading to. Okay? Right? So that's my point. Thank you, guys. Thank you, Khalid and Abdulaziz, for your input. So now one of the last things we have to see today is about the preconditioning, which is another beautiful idea. That's why I put this into another subsection I called extensions. Sometimes the idea is to do some kind of preconditioning to find a nearby problem that can solve the problem, which is AX equal B, much faster. So for a given matrix A, the idea is to choose a simpler matrix B that is close to A. So in fact, you would multiply the problem by kind of P minus 1 two sides. So you get p minus 1 ax equals p minus 1 b instead of ax equals b. So there are several flavors here on the menu. You have the Jacobi iteration, in the case the p you chose is a diagonal matrix. You have what you call a Gauss-Seidel method. In fact, you've chosen if you've chosen a triangular matrix. You have an incomplete LU. If p is just an incomplete LU elimination factor, obtained by an incomplete LU factorization, or what you call a multi-grid method, which in fact is based on a Corsa grid. Right? So it uses the same difference matrix as A, okay, but on a Corsa grid. So it's kind of using a smaller mesh, or smaller, let's say, precision. Right. So that was the one of the last things. The last thing is about the what we call Kaczmarz iteration. So the Kaczmarz iteration is quite close to the idea of the conjugate gradient. So for this algorithm, the convergence is exponentially fast with high probability when the solution, the equation we're trying to solve is chosen randomly. So here is the idea is very simple. At every step k, this algorithm or this iteration dives into the ith iteration or the ith equation. So in fact, xk plus 1 would solve the equation AIT times x equals BI. So we just take one row and try to solve it. One row of the system and try to solve it. So we will have xk plus 1 equals xk plus this mathematical piece, which is the solution, in fact, to the equation, which you got here. Okay? So it's AI multiplied by BI minus AIT xk over the norm squared or magnitude squared of AI. So in fact, what happens inside it is that each step projects the previous xk onto the plane AITx equals BI. And if you cycle randomly through the m equations, you are in fact, if you are the cycle, sorry, in order, we have the classical Kaczmarz, and if you cycle random and randomized order, you have a faster convergence. So, but you can choose, in fact, the row I you're trying to solve using either a uniform distribution or just a probability, which is proportional to the norm of AI squared. Okay, so you have kind of let's say a distribution that gives more importance, more probability, depending on the norm of AI squared. Okay, so the higher is AI in norm squared, then the higher probability to choose this equation, because it's telling you you are just interpreting this magnitude as the importance of the equation and the system. So the Kaczmarz iteration, in fact, is an important example. When we have to deal with these kind of new methods, we call them stochastic gradient descent methods, because in fact the equation you will solve at every step is randomly chosen. So basically, this is, you see, this is a part which is a little bit heavy. I'll probably do later on 1 or 2 examples manually of these algorithms. Okay, but I wanted to close that chapter, this section, sorry, where I cover the section 2.1, inshallah. Okay, so any other notes to add, guys, before we leave?